Have you ever seen something so small, so completely ordinary, that it just kind of breaks your brain a little? And you start wondering, okay, how far can this little thread of curiosity actually go? Well, we're about to dive into one of those exact stories. It's a journey that, believe it or not, starts with a piece of candy trash and ends up asking questions about the very fabric of time.
I mean, when you think about it, some of the biggest aha moments in history didn't happen in some fancy high-tech lab, right? They started with, an apple falling on someone's head or steam pushing the lid off a pot. And in this case, it all started with a chocolate wrapper stuck to a pen cap. It's just a perfect reminder that sometimes the biggest, most profound questions are hiding in the most ridiculously normal places.
So that leads us to the central, and let's be honest, kind of absurd question of this whole thing. It really does sound like the setup to a joke, doesn't it? What does a chocolate wrapper have to do with the fabric of space-time? But I promise you, the answer is way stranger, and frankly, a lot more interesting than you'd ever guess.
84 days. This is the number that starts this entire wild ride. So get this, a pen cap gets briefly magnetized and a chocolate wrapper sticks to it. No big deal, right? Except it stayed there, just hanging on, suspended, fighting off gravity with what should have been the weakest little whisper of magnetism. For 84 days. That's almost 3 months. For a soft metal that's supposed to lose its magnetic charge in like a few hours, maybe even minutes, this was just deeply, deeply weird.
All right. So when faced with this bizarre little puzzle, the author didn't just shrug and move on, which is probably what most of us would have done. Nope, they got methodical. They realized this wasn't just some random fluke to be forgotten. It was a real phenomenon that needed to be understood. So they started experimenting, trying to figure out the rules of this strange little magnetic balancing act.
The process itself was pretty straightforward, but they were super rigorous about it. Step 1, magnetize an everyday object. Step 2, attach something else to it, but with the tiniest possible point of contact. And then, the hard part, you just wait. The whole goal was to isolate all the variables and figure out if that 84-day wrapper was just a one-off miracle or if it was some kind of repeatable law of physics hiding right under our noses.
And this table here, it shows exactly what they found. It wasn't just the chocolate wrapper. A pen spring on some steel, a screw and a hair clip, totally different objects, different metals, and the result was always the same. Once the system found its perfect little balance point, it just stayed there, indefinitely. It would hang on forever until something from the outside came along and disturbed it. It's like a perfect little miniature version of Newton's first law. So naturally, the next step was to try and put some numbers to this, to quantify it. A formula was proposed that boiled it down to 4 key things: the material's magnetic memory, the area of contact, how long it was exposed to the magnet, and the weight ratio of the two objects. But here's the kicker. One variable, A for contact area, was the king. It was by far the most important factor. And this is the really counterintuitive part. The smaller the point of contact, the more stable the whole thing was. Pretty wild, huh? Okay, so we've got this repeatable thing happening, this stable magnetic equilibrium. Cool. But this, right here, is where the story takes an absolutely massive leap. We're going from a simple physics experiment on a desk to the very frontiers of theoretical cosmology. We're talking about connecting this humble little observation to the work of Albert Einstein himself. Now, to really understand this giant leap, we need to quickly touch on the core idea at play here, something called remnant magnetism. All that really means is the magnetic memory a material holds onto after you take the magnet away. And here's what was so strange. In soft metals, like the ones being used, that memory is supposed to fade super fast. But in these experiments, it just wasn't. And that lingering effect, that stubborn magnetic memory, is what led the author to ask this huge, powerful question. Look, Einstein spent the last part of his life chasing a theory of everything, a way to unite electromagnetism and gravity. So the question became, could this tiny experiment, this whisper of a magnetic force, perfectly balancing the constant pull of gravity, indefinitely, could it be a tiny clue, a microscopic hint pointing towards that grand unified theory?
And the reason you can even ask such a bold question comes down to how beautifully simple the setup is. When you look at that suspended chocolate wrapper, there are only 2 fundamental forces at play, locked in this delicate dance. You've got the weak electromagnetic force pulling up, and you've got the relentless gravitational pull of the entire planet pulling down. When you can isolate 2 of the universe's fundamental forces like that, in such a clean way, well, it just begs you to take a much deeper look. So once that door to fundamental physics was cracked open, it was like the floodgates of creative thought just burst. That one little question about gravity and magnetism, well, it spiraled, and it spiraled fast, right down a full-blown time travel rabbit hole.
The brainstorming kicks off with the biggest headache in all of time travel: paradoxes. You know, the classic grandfather paradox. If you go back in time and change the past, you could accidentally erase yourself from existence. So, what's the proposed solution here? Simple. You don't actually change your past. Instead, any trip to the past just splinters off and creates a brand new timeline, a whole parallel reality, leaving your original timeline completely safe and untouched.
Okay, so if we can sidestep paradoxes, what about the universe's biggest speed limit? The speed of light. Well, we all know Einstein's famous E=mc², right? It ties mass directly to energy. So the speculation goes, what if you could somehow mess with that fundamental link between gravity and electromagnetism to reduce an object's mass all the way down to zero? Could you essentially unanchor it from spacetime and just go faster than light? And that chain of thought brings us right back to where we started. In a way, if magnetism and gravity are linked, and we know from Einstein that gravity bends time, then could a really powerful magnetic field have a direct effect on our perception of time? I mean, think about it. We've got iron in our blood. Are our own bodies maybe susceptible to these forces in ways we just don't understand yet?
This line of thinking even led to a pretty detailed, though, speculative experiment. Picture this. You take a giant magnetic sphere and you place it at a Lagrange point in space. That's one of those weird, perfect spots where the gravity from the sun and the earth completely cancel each other out. Now, what if you put a person inside that sphere? In that unique zero-g but not really state, would they feel a change in their mass, or even a change in how they experience time itself?
Now, before you dismiss all this as just pure fantasy, I want you to remember this number, 0.02 seconds. That is how much younger cosmonaut Sergei Krikalev was after spending 803 days in orbit compared to us down here on Earth. Why? Because he was moving so fast, time literally slowed down for him. Time dilation is not science fiction. It is a proven, measurable fact of our universe.
So with all these paradoxes and problems, a kind of safe time travel loophole was proposed. The idea is, forget about going to the past. It's just too messy. What if you only ever travel into the future, using stuff we know works like time dilation? You could go forward, observe, don't touch anything, and then just return to your original point in the present. You'd get to see the future, but with absolutely zero risk of messing up your own past.
Okay, wow, that was a pretty wild ride, wasn't it? From a piece of foil all the way to the very edges of theoretical physics. So after all of that, what's the point? What's the big takeaway we're supposed to get from this whole journey of curiosity?
It really is this. The journey itself is the whole lesson. It shows that starting with a simple, stubborn why about the most normal, everyday thing can literally lead you down a path to questioning the fundamental laws of our cosmos. It is the ultimate testament to the power of a curious mind.
And who better to summarize this whole idea than the man whose work inspired so much of this in the first place? Albert Einstein himself said it best. He believed curiosity was basically a force of nature all on its own. It doesn't need a reason to exist. The value is just in the act of questioning.
So I'm going to leave you with this final thought to chew on. Where exactly is the line? At what point does a simple question about a chocolate wrapper stop being a quirky little project and start becoming real, potentially paradigm-shifting science? And maybe the more important question is, does that line even matter at all?